Today, we're diving deep into the world of some pretty extreme manufacturing. We're talking about how the components for things like jet engines, aircraft wings, and even rockets are actually made. These are metal parts that have to be impossibly strong, but at the same time, incredibly light. Getting that combo just right is a serious engineering puzzle. So let's get into it and see how it's done.
So, right off the bat, here's the core problem. Think about it. When you're building something that needs to fly, every single gram matters. But the forces trying to rip apart something like a wing are just immense. You need the strength of steel, but without all that weight. The secret is in aluminum alloys. But to really unlock their full potential, you need a process that honestly sounds like it's straight out of science fiction.
And here's the thing. There is absolutely zero room for error. The heat treatment that gives these aluminum parts their superhero-like strength has to be controlled down to the degree. But even more than that, you're in a frantic race against the clock. The second that metal leaves the heat, a timer starts, and you have just a few seconds to lock in those properties forever.
Okay, so how on earth do you solve that speed problem? I mean, you can't just wheel a giant glowing hot airplane part out of a normal oven. It's way, way too slow. The solution is as dramatic as it is brilliant. You don't take the part out of the furnace, you drop the furnace out from under the part. And this is it, the drop bottom furnace. Yeah, instead of a door on the side, the entire floor just opens up. The heated aluminum part, which is sitting on a platform, gets plunged straight down into a massive tank of water or a special polymer solution that's waiting right below. It's this vertical, gravity-powered move that is just brutally efficient. Let's just walk through the play-by-play. First, the part gets heated up and soaks at an exact temperature, sometimes for hours, just to get its internal molecular structure perfect. Then the action happens. In a split second, the floor doors slide open, the lift mechanism lets go, and the whole thing drops instantly into that quench tank. It's that sudden shock that locks the metal structure in its strongest possible state. This, right here, is the magic number. The entire transfer from the inside of that furnace to being fully submerged in the quench tank has to happen in 5 to 10 seconds. That's it. If you're any slower, these tiny, microscopic weaknesses start to form in the metal. And you can imagine, at 30,000 feet, those tiny flaws could be absolutely catastrophic. So this speed isn't just a goal, it's a non-negotiable, critical safety requirement. So being able to hit that 10-second window over and over again with a part that weighs tons and is heated to hundreds of degrees, well, that takes some seriously robust engineering. So let's take a look under the hood at the components that make all this possible. The best way to think about one of these furnaces is like a high-tech fortress designed to contain heat. On the outside, you've got this rugged steel frame for pure strength. The inside is lined with stainless steel to fight off all the wear and tear from constant heating and cooling. And then it's packed with layers of ceramic fiber and mineral wool insulation, which keeps the heat exactly where it needs to be, making the whole system surprisingly energy efficient. Now, for the actual drop, the execution has to be flawless. The doors slide open horizontally, and they're powered by systems with all sorts of safety interlocks to make sure nothing goes wrong. The lift mechanism, which is either pneumatic or hydraulic, is really the heart of the whole operation. It's engineered to react instantly and reliably, even when it's dealing with extreme heat. And the whole thing is perfectly integrated with the quench tank below, making the drop a single, seamless, automated event. But here's what's really cool. It's not just heavy machinery. It's a smart system. It's all run by a PLC, a programmable logic controller that acts as the digital brain, automating the entire sequence for perfect results every single time. Dozens of thermocouples are constantly monitoring the temperature, making sure it's uniform to within plus or minus 6 degrees Celsius across a huge part. And every single second of the process is logged, creating a digital birth certificate for each component. That data trail is absolutely essential for passing the strict audits required by aerospace standards. Achieving this level of precision is a really specialized craft, and some companies have basically turned it into an art form. So to see how all these pieces come together in the real world, let's take a look at a leader in this space, a company called Electrotherm. You see, for a company like Electrotherm, complying with incredibly strict standards like NAD CAP or AMS 2750F isn't just some feature they add on. No, it's the absolute foundation of their entire design. In the world of aerospace, if you can't prove your process is perfect and repeatable every single time, you're not even in the game. You simply aren't allowed to supply the parts. And right here, you can see how they deliver on that promise. They don't just meet that 5 to 10 second quench window, they guarantee it in 7 seconds or less. They use high-velocity fans and multiple heating zones to nail that critical temperature uniformity. They also offer a huge range of sizes for different parts, and they build their machines to last and be easy to maintain, because in manufacturing, downtime is poison. It's a fully automated system built for one thing: certified perfection. So let's zoom out for a minute. What does this highly specialized piece of equipment really tell us about modern, high-stakes manufacturing?
While a company in this field doesn't just sell you a furnace in a box and wish you good luck, they provide what's called a turnkey solution. With a history that goes all the way back to 1936, companies like Electrotherm, they handle everything, from the initial design and development to the manufacturing, the installation, and all the service that comes after. For a customer building critical aerospace parts, that kind of end-to-end partnership is just as valuable as the machine itself. And this gives you a sense of where they fit into the global market. As you can see, while some of the top American producers might sit at a slightly higher price point, Electrotherm positions itself very, very competitively. They offer that same high-quality, fully certified technology that meets all those non-negotiable standards, but often at a more accessible price. It's a strategy that's all about delivering that perfect balance of world-class performance and real value. The drop-bottom furnace is really a perfect example of a hidden technology that makes our modern world possible. It's an incredible piece of engineering that most of us will never ever see, but it's quietly forging the backbone of the airplanes we all fly in. It kind of makes you wonder, doesn't it? What other invisible technologies, born from this kind of incredible ingenuity, are out there holding our world together?